So, next we will show you the permittivity, that equipment in which we determine the transmittivity. So, this equipment is the full length in plane flow. So, now we will show you the equipment how you can determine the transmittivity of the geocentric material. So, this is the your full length in plane flow, and here the size of the sample will be 200 divided by 100 millimeter, which is located in between the two plates, and then you are applying the load, and then you are measuring the what will be the head. So, this is the kind of the equipment we use for the determination of the full length in plane flow. On the other way also you can determine that what should be the transmittivity of the geosynthesis using the radial in plane flow. So, this is from the center the water is passing radially. Okay. So, this is the kind of geosynthetic material is here, and this from the center water is passing and going through radially, and then you can see the head difference, and then you can determine what should be the transmittivity of the geocentric material using the radial in plane flow, because in case of transmittivity water will pass along the plane of the geocentric material. So, procedure that trim the specimen to required dimension and place it over the test device and device base, and then still the side of the specimen parallel to the direction of the flow, and place the top plate on the test assembly, applying the small sitting stress of 5 to 10 kilopascal. Slowly fill the reservoir, allowing the water to flow to the test specimen. When the steady flow through the specimen is observed, record the time taken by 0.005 meter cube of water to pass through the specimen. If the time exceeds that 15 minutes, record the quantity of water collected in 15 minutes. So, you can repeat the test with increase the compressive stress, and then you can calculate what will be the flow rate per unit with Q is equal to capital Q by W, where capital Q is the discharge per unit time and W is the width of the specimen. So, hydraulic transmittivity psi theta is equal to Q into L divided by W into H, where Q is the discharge per unit time, L is the length of the specimen, W is the width of the specimen, and H is the differences in the total head across the specimen. So, if you know what will be the quantity of water, you know the what will be the length of the specimen, and also equally you know what will be the width of the specimen and what will be the difference in the hydraulic head of the specimen. Then you can calculate the what should be the hydraulic transmittivity of the geosynthetic material. For an example, in a one specimen calculation, that if the length of the sample of the geosynthetic material, let us say L of G, is equal to 200 millimeter, and width of the sample, let us say, which is designated as W of G. So, this is equal to 100 millimeter, and the thickness of the geocentric material, let us say T of G, is equal to 0.5 millimeter. So, you have to determine what will be the flow rate. That means flow rate is equal to Q. You can measure flow rate is equal 1 into 10 to the power minus 6 meter cube per second. So, you are measuring the flow rate when you know what will be the quantity of water collected at a particular time. So, you know what is the volume of water collected in the reservoir for a particular time. So, you will be knowing what will be the flow rate, that is Q. And let us say that head loss is equal to 10 centimeter. So, you know the equation theta is equal to Kp into T of G is equal to Q divided by W into I. Again this is equal to Q divided by this is W of G. So, this is W of G into delta of H divided by L of G. So, theta is Q is equal to flow rate, that is 1.10 to the power 1 into 10 to the power minus 6, that is Q. This divided by W of G is equal to 100, this is 100 into let us say 10 to the power minus 3 into delta of H. So, here that this is about head loss is 10. So, this you can write 10 into 10 to the power minus 2 all in terms of the meter, and this divided by L of G. So, L of G is 200 millimeter. So, this will be equal to 200 into 10 to the power minus 3. So, this will give you 2 into 10 to the power minus 5 meter square per second. So, ultimately you can determine what should be the K of P, K of P. So, Kp will be equal to your theta divided by T of G. So, we can write K of P is equal to theta divided by T of G. So, this theta is 2 into 10 to the power minus 5 and this divided by Tg. Theta is 2 into 10 to the minus 5, this divided by T of G. T is 0.5 millimeter. So, you can write 0.5 into 10 to the power minus 3. So, this will give you that Kp value 0.04 meter per second. So, you can determine that what should be the transmittivity of the geosynthetic material. So, this is the transmittivity of geosynthetic material is 0.04 meter per second and unit is meter per second. In case of permittivity, unit is per second. In case of transmittivity, unit is meter per second. So, you can determine what should be the permittivity of the geosynthetic material. So, these are two important. One is the filtration, when you use the term that what is called the permittivity of the geosynthetic material, when the water flow across the plane of the geosynthetic material. So, you can determine what is theta p and unit is per second, and in case of transmittivity, when the water flow along the plane of the geosynthetic material, and you can determine what will be the transmittivity of the geosynthetic material, and unit of transmittivity is meter per second. So, next we will discuss the apparent opening size or AOS or equivalent opening size of the geosynthetic material. This is as per ASTM D4751. And this is very important, the apparent opening size. You should know that how much quantity can pass through the geosynthetic material and how much material can retain in the geosynthetic material. So, it is exclusively used for the filtration and drainage, and this is very important test to perform the apparent opening size of the geosynthetic material. So, main objective of this test to determine the apparent opening size of a geosynthetic. The largest particle size that can pass through the geosynthetics is known as the apparent opening size of a geosynthetics. The O95 value is specifically used for the design for any hydraulic structure. The apparent opening size of the geotextile decrease with the increase the weight of the geotextile material. So, you can draw also that correlation between the apparent opening size of the geosynthetics. You know what will be the particle and what will be the O95 value from the gain size distribution curve, and then you determine what is apparent opening size of the geosynthetic material. I can show you that one, that this is the, for example, that this is the percentage passing, as you know, for gain size distribution curve, okay, and let us say this is 0, 10, 20, 40, like that, just say 80, just say 100, like this. And this is the millimeter, this is maybe that your fine sand, or it may be the coarse sand, okay. Let us say 0.2, 0.02. So, you can have the curve like this, you can have the curve like this for different types of the geosynthetic material. Let us say this is A, this is B material, and let us say this weight of this material 250 gram per meter square, and B material weight, let us say 300 gram per meter square. So, from this curve, for the 95 percentage will give you that what you call the O95. This is very important, O95, 95% of the soil retained. So, then you can determine what will be the apparent opening size or equivalent opening size of the geosynthetics material. And this apparent opening size of the geosynthetics vary from different types of the geosynthetics material. Now, we will discuss that percent opening size. So, percent open area can be defined as the ratio of the total open area or the total void area of the geotextile to the total area of geotextile material. So, it is expressed in terms of the percentage. So, percent open area is designated as POA, that is total area of the opening of geotextile divided by total area of geotextile. The open area is measured by passing a light through the geotextile to a posted side cardboard which is in the form of a graph sheet, and from the graph sheet number of the square can be counted. Otherwise, the void can be mapped by a planimeter. So, total area is measured by the same magnification. And next, that POA, percent open area, is applicable only for monofilament woven geotextile material. The percent open area for monofilament and slit film woven should be greater than or equal to 4%. As the filament of non-woven geotextile are closely tightened and very random, light cannot pass through it properly, and as a consequence the light passing method is not suitable for it. So, there are different types of the methods in which you can determine apparent opening size. Can be measured in the 4 ways: one by sieving the glass bead, or by image analyzer, that is given by Gauris et al. About 1982, and by Mercalli intrusion, that is given by Holz 1988, and by bubble point method, that is Bhatia 1996. So, different types of the method to determine the opening size. Equipment and the accessory that require, that is mechanical sieve set, and then pan cover and the sieve frame, and spherical glass beads and the balance. So, these are the pictorial view of the glass bead of different sizes. You can see here, this is the lead, and this is your vibration unit. This is a schematic of dry sieving method, and this is the pan, and this is the geotextile material which is tightened with this with the sieve, and this is the lead, and this is single size of this is the single size of the single size of the glass bead. So, geotextile is clamped at the sieve, and then beads is on the top, and you can shake in this machine, and you can determine that what should be the apparent opening size. So, for this procedure, secure the geotextile on the sieve frame such that it does not wrinkle or deform. Place 50 grams of the smaller diameter beads on the geotextile and sieve it in sieve shaker for 10 minutes. Wait and record the glass bead retained on the surface. Repeat the step using the larger bead until the weight of the bead passing through the specimen is less than 5%. So, that you have to remember, 5% passing through. And then you can draw the relationship between the percentage finer and the particle size, and it depends on the what should be the weight. So, this weight is 675 gram per meter square, and then for this O95 is very important. So, you can determine what is O95. So, this grain size distribution curve is vary from material to material. So, you can see one is the 675 gram per meter square weight, another is the weight of the sample is 700 gram per meter square. So, for this you can determine what is O95 for the red one, O95 for the blue one, and this AOS for the blue one is 0.17 millimeter, and for AOS for the 700 gram per meter square is 0.25 meter square. So, this value is very important, that what should be the apparent opening size of the geosynthetic material. We are to design that what material should retain on the geosynthetic material and what material should pass it through the geosynthetic material. So, this is used mainly for the filtration and drainage system, and apparent opening size is very important for also the any kind of the water flow related problem, erosion control related problem. Next, I will talk about the porosity, main objective to determine the porosity of a geosynthetic material, and porosity of a geosynthetic is defined as the volume of the void to the total volume of the material. It is usually expressed as percentage, and the procedure is that porosity can directly be determined using the equation. You know that porosity N is equal to volume of void divided by total volume, that is V of V divided by V. So, you can determine that if the total volume V is equal to Vs plus V of V. So, Vs is the volume of solid. So, this is equal to M into A, this divided by rho. What is M? M is equal to mass per unit area, that is gram per meter square, and A you know that is area and that is in meter square, and rho is the density. So, that is gram per meter cube, and VB is the volume of void. This is VB is the volume of void, and so total V will be the, that means this is total volume. So total volume is equal to A into T of G, where Tg is the thickness of geosynthetics. So, from this you can calculate that what should be the porosity of the geosynthetic material. So, N porosity, this is volume of void divided by V, is equal to V minus V of S divided by V. That means this is equal to 1 minus Vs divided by V. So, again N is equal to 1 minus, this you can write M into A divided by rho, this divided by this volume is equal to A into T of G, the thickness of the geosynthetic material. That means this you can write 1 minus M divided by rho into T into G. So, you can determine what should be the porosity of the geosynthetic material. So, you have to remember this equation 1 minus M into rho into G. I can give one specimen calculation for the determination of the porosity of the material. So, for the specimen calculation, so you know that let us say it is a non-open geosynthetic material and mass per unit area is equal to 258 gram per meter square. And let us say thickness of the geosynthetic material is 0.0023 meter. Now, you know the density is equal to 1.3 gram per centimeter square. So, porosity N is equal to 1 minus M divided by rho into T of G. So, you know this equation. So, you can write 1 minus M is equal to 258 here, mass by 258 into 10 to the power minus 4. This divided by 1.3 is the density rho, this into thickness of the geosynthetics is 0.23. So, you can determine that what should be the porosity. So, N value will be 0.9137. So, this way you can calculate that what should be the porosity. And next is the endurance properties of the geosynthetic material, that what is called the abrasion and ultraviolet degradation and clogging, what is called the gradient retrostage. And clogging is very important because you have to check whether the geotextile material has been clogged or not. So, abrasion test or abrasion resistance as per the ASTM D4886 and ISO 13427. So, main objective of this to determine the abrasion resistance of a geosynthetic material. So, wearing away of the geosynthetics due to rubbing against the another surface is called the abrasion. because geosynthetic material may be damaged when you can use for the railway construction, when the rail can passes and you are using the geosynthetic material for the construction of the railway infrastructure. So, there should be a load when you will passing through this material, then geosynthetic material there will be the rubbing. So, there will be the abrasion between the geosynthetic material and the granular material. So, that is why it is required that what should be the abrasion in order that geosynthetic material should not be tear up. So, it is determined that abrasion resistance of a geosynthetic material. So, geosynthetic specimen you have to keep in a disc shape with the inner diameter about 60 millimeter and the outer diameter about 90 millimeter. So, you can see here that you can see here the equipment and the accessory for abrasion test. This is the balance head and the block assembly, indicator for indicating number of the cycle, weight and clamping device. So, this is the kinematic abrasion resistance. Geosynthetic material is placed here and then this geosynthetic material vibrolift wheel and then it's rotate and geosynthetic material may be tear it up. So, procedure for this is that place the geotextile specimen on the rubber platform and clamp it properly and rotate the fixed abrasion wheel to abrase the specimen. The wheel is rotated up to 1000 cycle and cut the specimen and to determine what will be the tensile testing of the geosynthetic material due to abraded specimen. Also you determine what will be the tensile strength of the geosynthetics without abraded. Then you take the ratio of the tensile strength of the abraded specimen and the tensile strength of non-abraded specimen and that into 100 which will give you the abrasion resistance of the geosynthetic material. For an example, that specimen calculation, suppose type of geosynthetics is the oven geotextile material and tensile strength of the non-abraded geosynthetic material. That means, tensile strength of non-abraded geosynthetic material is 21.02 kilonewton per meter and tensile strength of the abraded geosynthetic material, let us say 17.28 kilonewton per meter. So, you have to determine what will be the percentage of the strength retained, after abrasion. So, this is 17.28 divided by 21.02, this into 100. So, this will give 82.20%. So, abrasion resistance is very important for the determination of the geosynthetic material, so that geosynthetic material should not be any damage. So we check up all these different types of permittivity, transmittivity tests. We talk about the apparent opening size of the geosynthetic material, we talk about the porosity of the geosynthetic material, we talk about the abrasion resistance of the geosynthetic material. So, this is very important, abrasion resistance, so that geosynthetic material should not be damaged. So, this test is very important.